Right, a little bit of admin. So I encouraged you to have a look at question 4, and I don't know if you have, and if you haven't, I would encourage you to. So this was on page 307, I think. So this was some examples of substitution using limits, where you had to work out your own substitution. And I said I'd do C, but actually B was really interesting. So if you used this substitution, u squared rather than u, I haven't tried it with u actually. Actually, do it with u. No. Okay, if you do it with u squared anyway, you end up with this. And actually, we've solved that with x actually using integration by substitution. So actually, you could sort of say this is a substitution within a substitution, but actually there's another way of doing it, and I have to say this, I've never really sort of done this before. If you think of that as partial fractions, order of this is the same as the order of this, so we have to divide first, and it looks really odd when you divide it. That divided by that, it's the shortest long division ever. You end up with 1, remainder 1. So actually that becomes that, which when you integrate it with respect to u, that becomes u, and that becomes minus the ln of that. So that was, I thought that was quite an interesting one, and that's in the solution bank. Did anyone do it with u instead of u squared? Perhaps I'll go away and try that one. And then for 4c, if you use 1 plus cos theta as your substitution, then du by d theta is minus sine, so you get that as your replacement. So d theta becomes minus du over sine theta, and I straight away pulled the minus out there. Cos theta is u minus 1. And then you just have to use the identity. Write sine 2 theta as 2 sine theta cos theta, so that sine theta cancels out with that sine theta. So you're left with 2 cos theta. Pull the 2 out, replace cos with u minus 1, so you get that. And that's 2 things divided by 1 thing. So you can write that as u over u, 1, minus 1 over u. And that works out quite nicely then. So that was actually, although when I looked at that, I thought that's probably the hardest. Actually, that was quite nice, still quite hard compared with that one. 4b was a bit of a mind scrambler. Anyway, I'll share the video with all of you. So if you haven't done those, I'd recommend that you do those. So that was that, and then we sort of finished last lesson. I don't know if it was a bit unwise to finish the lesson with it, with an introduction to this whole idea of integration as a limit. And I said we'd start today with this question, which is one of the 5 hardest questions that according to how badly they were done, that have ever been asked. So only 28% of people scored anything on this question. So it just looks horrible. It looks horrible. You've got a function that we know, the square root of x, and they sketched it for us, and they've done this funny thing with a strip somewhere between 4 and 9, and there's all sorts of guff going on, and then they end up saying, so what is the limit as the thickness of the rectangle gets smaller of this? And what they're saying is, if you take this area and split it into lots of rectangles and work out the area of those rectangles and add them all together, what happens is you make the rectangles really, 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 really thin, which means you get more and more rectangles. So what you end up with is just the area under the curve. So we know that we answer that question just by doing, it's not working, just by doing this. So the square root of x is the function, and I'm going to straight away write that as x to the half. And I can do that by just adding 1 to the power, dividing by the new power. So this whole question, with all that confusing malarkey, all they want you to do is that. Okay? So I think it's really important, and you may have got it down from your notes yesterday, that you in some way indicate in your notes that something that looks like this is just a really complicated way of asking you to do that. And once you've made a note of that, go on, do it for me. Tell me what the answer is, insert form. So this is integration as a limit. What happens if you take the number of rectangles and increase them to the point where there's so many of them that they have zero width? What does that add up to? Well, it adds up to the area under the graph, and we know how to work out the area under graphs. We do it like that. If you wanted to have a look at that again, I suggest to look at the video. You'd think if your football team was in League One, you wouldn't have to pay so much for the shirts, would you? 58 quid! My Christmas present. 58 quid! I could buy half the team for that. Increase the power, divide by the new power, remember the denominator flips to the top. Right, so we get x to the 3 over 2 divided by 3 over 2, which comes like that. So that is 54 over 3, and that is 816 over 3. 40, 38. Yeah, 54 over 3 is 18. Yeah, I just left because I'd already done it. I knew that the other one was going to be out of 3, so I left it. Yeah. Okay. Right. So that is all the things we can integrate. All right. And we've done a whole load of techniques, but still every now and then you'll get something that you can't integrate. So how do we find the area under a curve if we can't integrate. Finding areas when we can't integrate. Finding areas when we can't integrate. Now, if I was you, Jodie, that would be annoying.
I appreciate that.
Oh, good.
Or someone else to throw it in.
That made it any better at all. Right, okay, so now the irony is actually most exam questions using this technique I'm about to show you today actually give you a function that we can integrate. So case in point here, sec squared, sec x is on the formula sheet. So we can integrate it. But the reason they, that there is a reason why they ask you to do things that we can already integrate. But let's pretend we can't. Let's pretend we've lost our formula sheet, all right? And we want to know the area underneath this curve. Well, we know how to do it because we did it at GCSE when we wanted to work out the distance travelled from a velocity time graph. We split the area up into rectangles. Hang on. I haven't plugged it in, have I? That's not working.
Just in case.
Okay. So we split it into rectangles, or if we want to be a bit more accurate, trapeziums. So I'm going to split this up into 4 trapeziums, and if I worked out the area of those trapeziums, I'd get a pretty good estimate for the area of under the curve. Actually, if I did trapeziums, would I get an overestimate or an underestimate for this curve? You're absolutely right. Can you suggest why?
Because the line's like curving, underneath.
Yeah, so a trapezium, if I sort of enlarge it, is going to give you that area, and actually it's slightly less. Yes, yeah. Got it wrong this morning. Convex shapes. It's looking up from underneath. It's coming towards you, so it's convex. Yeah, convex will be an overestimate. It's not always over, because if the curve was this shape, then the trapezium would be an underestimate, and that's a concave curve. Anyway, that's and so to work out the area of each of those trapeziums, I say, right, let's take the 2 parallel sides. So this length here is the value of y at that value of x, and this length here is the value of y for that value of x. So take those 2 y values, add them together and divide them by 2, and then multiply by how far apart they are. And then I take that y value, add it to that y value, the y value at that value of x, add those 2 together, halve them, multiply by how far apart they are. And if I use the same width, then that's the same number as I've just multiplied by. And you can see how it's actually quite quick and easy to work out those areas. Actually, we don't need to do that, because there's a shortcut you can take. The shortcut we take is called the trapezium rule. The trapezium rule. So what I've said is I'm going to split my area up into 4 rectangles. It doesn't have to be 4 trapeziums. Sorry, it doesn't have to be 4 trapeziums. I could use 3, but let's do 4. So what that means is that I've got my starting value of x. I've then got 4 x values, the last of which is the end. So we call those x0, x1, x2, x3, and x4. Sorry. I'm going to just leave it labelled on there. Notice 4 rectangles, sorry, not rectangles, 4 trapeziums, 5 values, and that's a bit like fence panels, isn't it? If you've ever put a fence up, if you want 4 fence panels, you need 5 posts. When I work out the areas, I use this length and this length and this length twice, don't I? Because I use it in that trapezium and that one in both, but these I only use once. So I've got here, this is the y value, the height of that first line is the y value for that value of x, so I'll call that y0, and that's y1, and that's y2, and that's y3, and that's y4. So they're the lengths that I'm actually going to use to work out the areas. Again, 5 y values, even though I've got 4 trapeziums, and that distance there is the same, and we actually call that h, because it's sort of the height of the trapezium. So let's work out the y values. We can easily look at the x values because I want to go from 0 to pi over 3. So I've got to just divide that into 4. Well, if I take 1/3 of pi and divide it into 4, that's 1/12 of pi. So my x values are going to be 1/12 of pi, 2/12 of pi, 3/12 of pi, and 4/12 of pi, which is the same as pi over 3. So I want to work out these y values, and I can just get my calculator out and do sec is 1 over cos, so I can do 1 over cos of 0, 1 over cos of pi. However, we've got a little bit of a shortcut we can use. We can use the table function on our calculators, which speeds this a little bit up. So let's you don't have to do this, but let's use the table function while we're learning how to do this. I haven't told you what we're going to do with these numbers yet either, have I? So get your calculator into table function and type in as the function 1 over cos, or just either hit the fraction button and do what 1 on the top or cos on the bottom. So yeah, so menu, table, delete that. So I'm going to type in as my function 1 over cos x. I'm going to make sure I'm in radians, because I know whenever I'm working out anything to do with trigonometry, whenever I'm differentiating or integrating with trigonometry, I need to be in radians. So that's my function. And then I go to set. And I'm going to set as my start value 0. And my end value, pi over 3. Now, this is one of those places where the fraction button doesn't really work, so I'm going to do shift pi divided by 3. And then the jump, well, do you remember the jump was pi over 12? That was how wide our strips were. So I'm just going to do and then I press X, and then I go to table. So So my start is 0, so it was 0 to pi over 3, which is what I'm trying to work out the area between, and then the step is how wide the strips are. So each strip is pi over 12, which is I'll have to do the table over here. Now we're estimating, aren't we? We're estimating. So this is one place where, in general, we don't use exact values and our calculator memory. Every question in the textbook gives us a number of decimal places. So let's work to 4 decimal places and record those y values. So the y values are 1, no, sorry.
Why did you put 0 point on the first one?
Because I'm a doofus. Which we all know by now.
Just do little arrows.
Okay, so I've worked out my y values, which, if you remember, are these lengths here, which are the heights we use of our trapezium. So I've filled that table in, and in general, exam questions will have partially filled it in for you. So now I'm going to work out the area of the trapeziums and add them together, and for that I need to turn to page 7 on my formula sheet, because I don't actually need to do it manually. There's a nice rule. Okay, page 7 on my formula sheet. My formula books are in the other room, so I don't know if you've. Open up my electronic copy. Yeah, that would be a bad idea, wouldn't it?
Would it? Why? Okay, but football, Newcastle versus Ipswich. I think I'll win.
Except, I was thinking one. So why is that not? Have we got at least one formula book per table? Okay, it's in the textbook as well. Sorry, it's on page 300 and. So it's on page 318. Page 318. So the trapezium rule, as it's written in the formula book, looks a bit scary. So here's how I like to think of it. Oh, there we go. So there we go. Looks a bit scary. All this nonsense here. What it means is this, and it's approximately, because the trapezium rule allows us to work out an approximate area. It's a half of h. H, if you remember, is the width of the strips that we broke it into. So in this case, that's going to be a half times pi over 12. We've then got a big old set of brackets. They make them curly. I'm just going to write them like that. But we've got a big set of brackets enclosing everything. Within that big set of brackets, we've got 2 other brackets. This first bracket is y0 plus yn. What that means is the first y value added to the last y value. I call that y ends. So it's those two added together. So in our first example, that's going to actually be 3. So that's the y values at the beginning and the end added together. We've then got a second bracket with a 2 outside it, which has got this rather convoluted thing. That's just the other y values added together, y others. So in this case, it's that plus that plus that, not the ends, but the other ones added together. So 1 plus 0, 3, 5, 2, plus 1.157, plus 1.4, 2. And that's just a nonsense way of working out how wide the strips are, but you know how wide the strips are, you know, it's common sense. So I think it's a scary formula, but it's not a complicated, you know, if you can remember that, it's nice and easy. So go on, just type that in. The calculator will do it all for you. And because we're using rounded values, we would be foolish to write it any more accurately than the values we've used. So I'm going to write my answer to 4 decimal places. Just got to make sure you have all your brackets closed off. Should I get to 4 decimal places? Now, because in this case we could actually check it. We could integrate it and check it. We won't in this case, but one thing I can do is to use the integration function on my calculator, which we haven't really talked about for a while, but if you go to Math and then press the arrow key, you've got this integration function. So I can integrate 1 over cos x. I'll get to limits, there we go, between 0 and pi over 3. Now don't forget, our answer is an approximate answer, so we're not expecting it to be identical, but we're looking okay. We're looking okay. Now actually, when you use the calculator to work out an area like that, it uses the trapezium rule. It just does a gazillion trapeziums rather than just 4. So this is actually calculated in the same way, and it's just more accurate. And remember, you can't just, if you've got a question where you've got limits, you can't use that to get the answer. You've got to show your method, but you can use it to check. So, let's have a look at another example where we're asked to use this process with a function that we actually already know how to integrate. So we are on page 320, question 2. This question here doesn't look very good on this. Page 320, question 2. I can integrate the cos of 5 pi over 2. I can integrate cos theta. Cos theta becomes sine theta when I integrate it. So the cos of 5 over 2 theta is sine of 5 over 2 theta divided by 5 over 2, what you get when you differentiate the bracket. But in this case, we're asked to do it using the trapezium rule. And so this is what it would look like. So we're asked to fill in this table. So you've only actually got 2 missing values. So you could use the table function, but you could argue, well, actually, it's probably quicker just to do those 2 values separately. Make sure you're in radians, and it's the cos of 5 theta over 2. It's not the cos of 5 theta all divided by 2. It's the cos of 5 theta over 2. And we're asked to give our answers to the values in the table to 4 decimal places. And then once we've used those in the trapezium rule, we work to 3 decimal places. So I know it goes against everything I've told you to use rounded values, but in this case we are asked to use the rounded values when we plug them into the trapezium rule. How wide are our strips this time? Well, we've got strips that are 1/10 of pi wide, aren't they? So h is 1/10 of pi, pi over 10. I'm going to use integration. I'm going to do part D for you while you do parts A, B and C. So I've got 0.8 as the exact answer. And you're rounding your answer to 3 decimal places once you've plugged it in. So the most common problem here is finger trouble. You know, people type numbers in wrong, or they write 0 point rather than 1 point. So you know that those sorts of errors can often occur. So I wrote it as 5 over 2 pi. So that becomes sine of 5 over 2. Sorry, theta, 5 over 2 theta. Sine of 5 over 2 theta divided by 5 over 2. Substitute values in, making sure you calculate it in radians. Got an answer, Spell?
0.7584.
So 758, so is that 758?
Yeah.
3, because it says to 3 decimal places. But, I think that's right. And Jodie, over or underestimate? Yep, so this time the trapeziums are coming underneath the curve. It's not much in it, you know, it's pretty subtle, isn't it? So we're then asked, and this is why they give you a function that we can actually integrate. They want to, because it's quite easy to just plug numbers into a formula. So they ask for the percentage error in your answer to the trapezium rule. So this was our approximate answer using the trapezium rule. This was the actual answer using integration. Integration gives us an exact answer. So the percentage error, well, what we need to do to work out percentage error is we need to say, right, how wrong was our use of the trapezium rule? And let's put that as a fraction over the exact answer. So the exact answer goes on the bottom, 0.8 in this case. How wrong were we? Well, we were 0.042 out. Is that right? Yeah. And that gives it to us as a decimal, and hopefully you realise that multiplying that by 100 would give us the percentage. And in this case, it's an underestimate, but the process would be the same if it was an overestimate. We would say, right, let's work out just the difference. So we wouldn't make that positive or negative. We just say this is the error. In this case, it's an underestimate, so it's 5.25% too low, but we don't say minus 5.25. We just say 5.25. Five past? What would I do with them? So, no, it's 5.
That's why I read it's 50 actually.
Yeah.
Are you okay?
No.
What's it?
I remember it wrong.
Yeah, it's 5 times.
No, I wrote it there as well.
I just got the value of
I wrote it as 5 times 10 and I wrote it as 5 and 2 times.
Have a go at this one anyway. Well, I'll yeah. So you should read your own values. So Yeah, good. So we want it because find. Yes. Yeah. How did you? Never noticed that before. Yeah, I think that's just another memory. So I guess they give you that memory. That's a really good point.
So
Yeah.
is theta just like another x? Or
Yeah. So that's the variable. Yeah, that's right. Yeah, Beth and Tina have just noticed something which I've never noticed before. You've got on your you can't see it. You've got on your calculator a theta here, but that's just another memory. So don't use that in expressions. That's an all-purpose button. That one. Use that one. That's just if you've got a value for an angle and you want to store it in something that's memorable, you can store it in theta. That's all. So that's just another memory. So I'm sort of hoping that in the time we've got left, you can do the trapezium rule bit, and then this is quite a good one to do at home because you need to use integration by substitution. Can I just say, don't worry about this bit. You don't need to answer it. I mean, you can if you want to think about it that way, but I just got the exact answer using integration by substitution. Don't forget you've got to replace those values as well. But anyway, see if you can get A and B done. We're working to 4 significant figures this time, which is the same in this case as 4 decimal places. We've got, it's not always 4 strips, but we've got 4 strips, and this time H is a half. The width of the strips is a half. H is a half in this case, and you've only actually got one value missing, so I wouldn't use the table function. I just type in 1.5 arrow x and type the function in.
It kept saying error when I was doing that. It's not on the table now, but
Oh, right.
like when I was doing this, it just what I'm doing.
Try put 2. Try putting a multiplication sign in between the x and the square root. Try putting 2 minus x in brackets. Sometimes it just gets as big as news. That works for me. So let's just
That's weird.
what's going on there? Now, if I think it's really worth finishing this one off. So that's the answer. Sorry, no, that's the answer to the area. Don't worry about the formula you want it, you'll get it. And that's the percentage. So I've started off, and again you can look at the video, can't you? I've started off the exact answer. I'm using integration by substitution. I changed my values to u values, and then you've got that odd thing where this is now smaller, but you still do that one first. So that's going to give me my exact answer, and then you're going to do the error over the exact answer. You should get 11.4. So see if you can get that question finished off. I sent out that PDF with the links. It seems like they're working. Tell you what, that's brilliant. That's absolutely, I think that's a great resource. And can I again really highlight? I'm trying to sort of get it in your head now. The importance of Easter. I'm not saying quit your jobs altogether and all that sort of thing, but just try and get the balance right, because that Easter is such a important time. And I know it's a sacrifice for if you want to be sat in the sun on a day like today, but maybe you're going to study instead. But you've got the lockdown aside, you've got the longest summer holiday you will probably ever have ahead of you. And I'll tell you what, you show me your sacrifice, I'll show you mine. It's my 25th wedding anniversary in May half term, and my wife and I were always going to go away, but we're saying, no, we're going to stay here so I can be on the computer ready to answer all your questions. So, we'll all sacrifice together, because at the end of it we're going to enjoy it. My summer won't be quite as long as yours, but I'll enjoy it every bit as much. So there we go. So try and get it in there. I know a lot of you got jobs, and I'm not suggesting for 1 minute you should quit those jobs, but just try and be sensible about your commitments. And as I say, I'm up to my biscuit game for next Wednesday, so we're definitely going to do circles. Any other requests? Otherwise, I'll suggest something on Monday, and I'll send out the questions. Here we go.